Hey everybody, it's Dr. J, and today we're talking about entropy. Let's talk chemistry. All right, so first thing I want to cover is that entropy is a state function. If you don't know what a state function is, basically go check out the General Chemistry 1 playlist. That's all I got to say. All right, state function. But basically, a state function, we care about the initial and final values. All right, that's it summed up in like 2 seconds. Now, let's talk about entropy, right? Entropy, let me give you the definition of entropy. Entropy is the dispersal of energy and matter, right? And in this case, it's being described by the state function entropy. All right, so when we're talking about entropy or S, right, we're just talking about dispersing energy, right? So if we look up here, the final state of a system is actually favored, right, if our energy can be dispersed over a greater number and variety of molecules, and the particles of the system can be more dispersed. So basically, what we're going to find out is that energy likes to be dispersed, right? It likes to spread its wings, it likes to fly, right? It believes it can fly. So it likes to be dispersed, right? It doesn't like to sit still. We like to disperse energy. And essentially, this is what, entropy is, the dispersal of that energy. So basically, if you have a large amount, right, if you have a greater amount of energy that you're dispersing, right, in a system, then that means that you're going to have a high entropy. So the more you're dispersing, the higher your entropy is. Or, right, another term we could use is basically disorder, right, which is also the dispersal of energy and matter. Okay, so basically, if you're more disordered, then you're going to have a higher entropy. So basically, for example, if we look at ice, right? Ice. So you got to think about a couple different things here, right? Ice, we understand, is a solid. We understand that solids are also, based on the stressor, very organized, right? They're ordered, they're compact, right? If you forgot about solid liquids and gases, go back to the very, very beginning of this playlist to check those out. Okay. But essentially, right, we look at ice, well ordered. But if we add heat to it, right? Now we added some energy, right? We're adding energy. That ice will become disordered. What happens is it's going to become that liquid, right? In this case, liquid water. And we understand, right, those atoms, those compounds, right, together are a little bit more free flowing, right? They got a little more room to move. And then if we add even more heat, energy, right? That means that the water will then, that liquid water becomes water vapor. And we understand what gases, right? Gases are just independent. They're going around everywhere, hitting everything constantly, right? And once it's in a gas phase, this is the most disordered phase of them all, right? And therefore, this is our highest entropy when we're looking at entropy compared to all three of the phases. In this case, right, that energy is not being dispersed when we're in our solid, but if we compare it to gas, where that energy is now disordered, dispersed out, right? Now we got a high entropy. The key thing though about entropy, so unlike our good friend enthalpy, another safe function, right? I highly recommend looking at those previous videos and General Chemistry 1. But yeah, unlike enthalpy, entropy can actually be defined, right? Because with enthalpy, you cannot define enthalpy in this case, right? That's the reason why we're using a couple of assumptions when we were doing Hess's law or enthalpy of formation or anything like that, right? So with entropy, we actually are defining it thanks to our third law of thermodynamics. Any pure crystalline substance at a temperature of absolute zero, so that's 0 Kelvin, has an entropy of 0. So now we got to define set limit, right? If you got a pure crystal and if it's at this temperature of absolute 0, then your entropy level will be 0, period. All right, we got a definition now for this. And because we have a definition, that's going to impact a lot of different things now, right? Because now we have a defined exactly moment for entropy. So when we're talking about entropy, right, let's look at this. So if you have a positive value for your entropy, all right, if you got a positive value is going to tell you that basically we're increasing in a reaction, right, or transformation, whatever you want to call it, right? If our positive entropy, that means that we're getting more disordered, right? And basically, right, as we mentioned before, that's favored, right? That's highly favored, right? So the Mother Nature, the Most High, whatever you want to call it, right? They like to disorder entropy, right? We like disorder, right? We like to spread that energy out. So when you're spreading that energy out, right, your entropy is going to be positive. Now your entropy is going to be negative. Okay, in this case, when it's decreasing, right, in the reaction or transformation, right, in this case, you're becoming less disordered. So basically, you're becoming more ordered, right? Now, Mother Nature, right, she don't like this, all right? As I mentioned before, they like the dispersive energy. If you're not dispersing energy, then you're decreasing your entropy overall.